now. And I don't really need to get back to Moodle, but I'll just kind of go back to Moodle to show you where we are. And also, there are certain things, you might want to read in the instruction for the demonstration. So we'll go there. And I'm still logged in because Moodle keeps my session even though I changed PC. cisp310. And this is the documentation of what I'll be demonstrating today, and also a little bit of explanation. The toolchain we'll be using is actually not GCC. Until the end of the semester, we'll get back to GCC. But what I want to do is to explain, why, what C and assembly language have in common. Both of these are quote-unquote compiled languages. In other words, the code that you write is not interpreted on the fly when you execute a program. Python is interpreted. PHP is interpreted. Perl is interpreted. In other words, with those programs, you write the program in a text file, and the interpreter is going to interpret one line at a time in order to find out what it needs to do. Now, there are advantages to that, being, when you are writing or modifying code on the website, you don't need to take the website down, recompile, and then bring the website up. Okay, you can basically just edit one file, and for the most part, the website will still work correctly. The rest of it will still work correctly. But the downside is it's very inefficient because you're doing translations over and over and over again, even though it has been translated 20 billion times already. It will still translate one more time if you need to execute that line.
What exactly do you mean by interpreted?
Interpreted means there's a program, the interpreter as a program will look at the source code, which is the text representation in high level, and it will decide what to do, and execute the proper subroutine for that. We are not going to use any GUI or TUI. Okay, GUI stands for Graphical User Interface, and TUI stands for Text User Interface. So we're not going to use any TUI either. We actually get to see the details of how programs are compiled, linked, and debugged. There's no single button on the GUI and say, click this button and it will run the program. No, not quite like that. Okay. Before we do anything, we have to edit or create the programs in text first. I'm not going to use assembly language for now. I'm going to use C for now, just for the demonstration. In Linux, the extension is not really that important to the operating system. However, to GCC, it is important. So that's why we still want to observe conventions of using a .c to mean it is a regular C source file, and .s to mean it is an assembly source file. We'll get to that part later, but for today, I'm just going to use a C source file. So I'll go to one particular terminal here. If you are using the virtual machine that we talked about last time, and you want to open up multiple terminals so that you can use one for editing, one for compiling and linking, and use another one for debugging, you can use Putty. Okay, so the way you use Putty to connect to the virtual machine is exactly the same way as using Winscp to connect to the virtual machine. Port 2200, I think, and localhost, and then the username and the password are the same too. All right, so I'm gonna make an example. Okay, so we'll say demo 1. I'm gonna increase the font size because there are people kind of in the back. Appearance. Go. All right, so I'm going to write a very simple program in C. It doesn't really do a whole lot of useful stuff, but it's a good demonstration. So we'll go ahead and say test.c. Okay. I'll include stdio.h, int main. Well, I'm going to use a subroutine here too. So we have a subroutine f, and it will just do a printf of hello.
Hello. Oh, saying hello world.
Yeah, just hello is fine. And in main, I have a local variable I, and we'll just do it like 3 times. Okay, for I equals to 0, I is less than 3, plus I, and then we'll call the subroutine F in here. So it's a very simple, short program. It's going to print hello exclamation point 3 times. Okay, not complicated. But the main point is not the program itself, but how to use the tool chain to compile, to link, and also to debug this particular program. So we save the file, and by the way, there are 2 editors in the virtual machine. One is VI and one is Nano. VI has a steep learning curve, okay, so you probably have to watch a few tutorials and have online help or printed help on the side just to kind of get used to it. For the first week or so, you will probably need a lot of help and time to do it. Nano, on the other hand, is pretty easy to work with because all the important hotkeys are labeled at the bottom part of the screen. So you can basically learn on the fly with that one. It's pretty easy to use. And for those of you who insist on using a graphical user interface editor, you can use Winscp. Winscp has a built-in editor, and you can create files and change files remotely, remote from the perspective of the virtual machine using Winscp. So that's the 3rd option if you want to use that option. But in class, I'm just going to use VI. Yep. VI and VIM. VI is kind of like the basic editor. It has most of the features, but certain features you can only find in VIM. Now VIM is actually, it stands for VI improved. So there are certain features that you can only find in Vim, but not in VI. In the virtual machine, it is up to you. If you like Vim, you can go ahead and install it. It's not installed yet, but you can just type as root, if you type aptitude install Vim, that will install it. All right, so we have a source file, which is just a regular text file. And I can, I can do a ls-l. -l means long format. And you can see that I have just created a file called test.c, and the file size is 130 bytes. Okay, the rest of it, not really that important in this class, so I'm not going to explain that. So the first step is to translate this into machine code using a compiler. Okay, now that part is explained down here. What is compiling? Now with compiling, it looks like there's a lot more explaining than it needs to be, but it's really not the case. If you look at one executable, a program that you can run as a book, okay, that book usually has multiple chapters. Okay. Has anyone read a novel that has, let's say, 300 pages, but it only has one single chapter? It's not broken up into chapters.
It's like House of Leaves, supposed to be like that.
Really?
Yeah.
But most books are divided into chapters. Textbooks divided into chapters, novels broken up into chapters, how-to books usually broken up into chapters too. So that's because it's easier to deal with chapters instead of the entire book from the perspective of the writer and also from the perspective of the reader. Compiling is the process of translation. But when you're writing programs, you'll be writing programs in quote-unquote chapters as well, except in this case, a chapter is one source file. That implies a lot of programs are written in multiple source files. There are 2 main reasons why we want to write programs in multiple source files. First reason is you can reuse code. In other words, if you have written certain subroutines to do, I don't know, sorting, okay? Sorting and searching and stuff like that. That's pretty universally useful, right? If you write that code in one particular source file, then you can reuse those subroutines in another project. You can either do a symlink, or you can just copy the source file to another folder, and now you have 2, 3, 4 projects sharing the same subroutines of sorting, searching, or some of the other things that you want to do all the time. That's the first reason. The second reason is it's easier to organize things this way. If you have most commercial programs are pretty long. Okay, let's say 200,000 lines. That's a pretty small program. Would you rather have one single file that has 200,000 lines in text, or would you break it up into logical source files, maybe 50 or 60 of those? What is the problem of having one single file? Well, your editor will go a little bit slower, right? Because it has to load up, all that content. And two, it is harder to find things, because it's not logically broken up into, smaller units. So that's why, when you write a larger program, it is usually broken up into multiple source files. And each source file is kind of like a chapter in the book. The compiler compiles on a per chapter basis. So when you compile a program, it is just compiling one chapter at a time. And the compiling process basically just turns something in a form that you can read, like the program that we saw a little bit earlier, into a form that the processor can understand, okay, in binary code, in opcode. The problem is, from time to time, you might have chapters that contain references to other chapters. For instance, if you're writing a textbook, and we are deep talking about, let's say, binary addition, and someplace I want to say, binary addition can be implemented by logic gates, and I want to insert a reference and say, see chapter blah 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 on page blah 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 for more details of logic gates. Okay, that's common in textbooks. Okay, just so that when you encounter a term, it has a link back to the definition of the term, and you can have a more complete treatment of that term. Except when I'm writing that chapter, I have no idea of what is the page number of the topic that I want to refer to. Is that making any sense? The translator, which is translating source code into object code, will have exactly the same problem. It's like, I don't know where that page number is. I know how to translate individual C statements into assembly code or into machine code, but I have no idea where that other subroutine is. So what the compiler would do in that case is it will leave behind something. It will leave behind some tags to basically say there are unresolved references in this chapter. It would just make a note and say, on page blah 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 of this chapter, we have a unresolved reference to blah blah blah, so somebody else needs to fix this. Okay, but the compiler is not going to fix it, because the compiler is only translating on a per chapter basis. In when we use Linux, the way you compile a program is GCC, and -C means just compile, do not link. Just convert the high-level source code into object code. Now, object code contains all the machine code already, but it also might contain unresolved references. So let's go ahead and do that here. So GCC-C, and then the name of the source file. So in this case, the source file is test.c, and if I do an ls after GCC, you can see that now we have a new file called test.o, which is an object file. The object file is the translated version of test.c. It is a translated chapter, so to speak.
And what's the difference between object code and opcode?
Object code is the same thing. Yeah, object code is basically the same thing as opcode.
Ones and zeros.
They're all zeros and ones. Yep.
Okay.
All right. But it's not fully resolved yet, okay? And you might say, but you only have one source file here. How can you have external references? Did I have external references?
Yeah, you did. You did.
Standard file.
You didn't make use of standard.
Are all subroutines that I use here defined in this particular file? Which one is not? Printf. Okay, so printf is not defined here. So the translator, which is the compiler, when it goes through this source code, it will just make a note and say, at this location of the object code, there's a reference to printf that is not resolved at this point. Okay, but it will translate the rest into opcode, into machine code. Even though this will work, In this case, I'm going to rerun the command using the -G option. The -G-C thing, in Linux land is also called a switch. So -G is called a switch. So when you specify -G, the object code created by GCC will now have extra information. That extra information allows a debugger to go from the address of an instruction back to the line number in the source code corresponding to the machine code. So now the debugger has the ability to say, oh, you want to stop here? Okay, I know exactly where that is. Okay? And -G is really useful if you want to use the debugger. The next step is linking. Linking is basically putting all the chapters together and resolving all the unresolved references. So linking is done, in this case, using GCC itself. So GCC is not just a compiler, it can also link, in this case. So when you're linking, you use -O to specify the name of the executable. In this case, I want to name my executable, let's say just test with no extension. And then you supply all the object files to it. In this case, I only got one. Test.o is the only object file that I have created. Press the enter key, and now I have an executable. When I do an ls, now I have the executable called test. Okay, test is the executable it can run. Just to show you that we can run it, we can say /test. In Linux, when you want to execute a program or a script in the current folder, you have to specify // because the current folder, which is represented by dot, is not a part of what we call the path, the system path. So it doesn't know where to find it unless you say explicitly and say, hey, here in this same folder. And the program ran, it prints 3 hellos, no big surprises here. Are there any questions about the commands that we just went through? The editing using VI, Vim, or Nano, the compiling using GCC with -G and -C as switches, and the linking using GCC-O, to specify the name of the executable. So those are the 3 stages to get a program to a point where you can run it. Now I want to debug the program. Okay. To debug a program, which is really the highlight of tonight's demonstration, is to use GDB. If you have not used a debugger before or used the debugging ability of Dev C++ or CodeBlocks, you will start to learn it now, because in assembly language programming, there's no way I can write programs and debug programs without a debugger. Okay, maybe some of you can, but I cannot. I'll be honest, it's way too hard to debug a program without a debugger. So now we get into GDB. The command to get into GDB is just GDB test. Okay. There are many commands that you might want to learn in GDB, and I'll just kind of go through a little list here. I think these are the most common commands that you want to learn. The first one is break, which is abbreviated to B. So the boldface means you can just say B instead of spelling out the entire thing break. This allows you to set up a breakpoint, and you can give it a line number or a label to set up a breakpoint. And the breakpoint means when execution gets to that point, the program will pause. Okay, it will just basically stop, but it's not terminated. It will just stop to allow you to take a look at the variables, do some other stuff, and then you can continue execution if you want to. Okay. Next one is list. List allows you to basically list the source code. So this way, while you're in the debugger, you will still be able to refer to the source code and say, oh, you know what? I want to stop on that line next. Okay. Delete is how you remove a particular breakpoint. Okay. And every time you set up a new breakpoint, it has its own ID, a number. And when you use delete, you have to specify the ID of the breakpoint. That's how you delete a breakpoint. Step, or just lowercase s, I think it's case insensitive, but step will allow you to perform one statement at a time. So if you're at a breakpoint already and you say S and then you press the enter key, it will execute just that statement, and then it will stop again. Now step has a close relative called next. Okay. Next will do about the same thing. The difference is with step and the next instruction or the next statement is a function call, step will step into the subroutine. Next, on the other hand, will execute the function call but not stop in the subroutine that is being called. That's the difference between next and step. Advance is really useful because it allows you to continue execution until a particular line, and it is not sticky. So that means if you say advance to line 35, it will continue execution at full speed unless you have intermediate breakpoints in between, but it will get to line 35 and then it will stop. But it's not sticky, so that means it will only stop this time on line 35 because it really is not setting up a permanent breakpoint on line 35. So that can come in handy when you just need to do a one-time breakpoint to stop, but you don't want it to stop all the time on line 35. We have continue. Continue means continue execution at full speed indefinitely until you get to a breakpoint or until the program exits. So continue really just means it'll continue at full speed. Inside GDB, if you want to, at a breakpoint, you can change the value of variables. And that comes in really handy because let's say your program is faulty, okay? And at a certain point, you look at the variables and you say, oh, this variable is supposed to be something else. But you want to continue the execution of the program just to see whether that will fix the problem. You can actually use set var and then the name of the variable equals to whatever expression to change the value of a variable in your program. So when you continue execution, the variable will pick up the new value. And it really just helps, when you're dealing with debugging. You can use print to print any expression in C. So XYZ is just a placeholder for any expression that you can specify in C. It can even be a structure. If XYZ turns out to be a structure, it will print out every single member of the structure, which comes in really handy. Now, up to this point, everything that I have explained, do you think is only usable in assembly language programming? Everything can be used in C programming, C++ programming as well. X is kind of interesting. It allows you to examine the values of certain memory locations. It is a very useful command. It's a little bit advanced, but in assembly language programming, the command X is particularly useful. And of course, if you want to get the whole program started, you need to run it. So R is just going to start the execution of a program. So these are the most common and I think the most useful commands in GDB. There are other ones too, but these are the very basic ones, and you just will use these over and over again. And now we get back to GDB here, and we start with the L to list the program. So if you want to list some more, just say L, enter again, and it will continue to list. If you want to go back to a certain point, you can just give it a line number. So in this case, I can say, oh, let's go ahead and relist around line 5. So it is actually relisting, not starting on line 5, but it's listing around line 5. Line 5 is the center of what is listing. Okay. So at this point, I want to set a breakpoint on line 5. Right before the printf, I wanted to stop and I want to do certain things. Okay. So the way to do it is to say B5. B for break, and then the 5 identifies the line number where I want to insert a breakpoint, which is line 5. And it tells me this is breakpoint 1. Now, the 1 is useful because if you want to remove this breakpoint, you have to say D1, delete breakpoint 1. And now I can start the execution of the program using R. And R normally will run the program at full speed until it gets to a breakpoint or until your program exits. So in this case, I have a breakpoint on line 5, and naturally it stops on line 5. I can now do other things. Okay. One thing I did not show that is actually also two commands that I did not show is useful in C, C++ programming. It will be useful in assembly language programming, but not for the time being. It's called backtrace. Okay, backtrace is abbreviated to BT, and what it does is it shows you how you got here. We are currently in subroutine F. Well, I know that part already because the breakpoint is on line 5 and line 5 is in subroutine F. But the question is, how did I get here? This shows me that I got to subroutine F currently on line 5 because on line 14 of main, it called this subroutine. Now that is a really useful feature, especially when you are dealing with, guess what? Recursion. Because in recursion, you will see the same subroutine appearing multiple times. And each time it appears, it will give you the ability to look at the parameters as well as the local variables of each and every invocation. So if you're dealing with recursion, that becomes a very useful tool. Yep.
And so the significance of the numbers on the far left, like the 0 and the 1, the 0 represents our current location. Like
You mean
the dollar
this
sign.
number?
Yeah, that.
Okay, that is referring to the frame number. The frame that you're in at this point, which is representing the invocation that you're in, is frame 0. So you're 0 frames away from where you are at this point. So frame 1 is 1 frame away or 1 invocation away. Frame 2 is 2 invocations away. Frame 3 is 3 invocations away, and so on.
Okay, so we would read it like the being 1 invocation away from where we're currently at is always going to be the call.
Yep.
Yeah.
Yep. Now the next command is really useful. Not so much in assembly language programming, but in C it is really useful because once I have identified that main is calling me, I can now change my current frame of reference from frame 0, which is the invocation of F, back to main. So to do that, I use the command called frame, and you just apply the number of frames that you need to get back to, and this shows you that we are F itself, or the invocation of F is frame 0, and the invocation of main is frame 1. So if I want to go back to main to look at local variable I, this is how I can do it. Now I'm back to main, and you can see that the current line in main is line 14. It doesn't change the point of execution. The program is still stopped or paused in F. It just gives me the ability to shift my perspective back to main, the caller of F, so I can examine local variables and parameters, if there's any, from the perspective of main, the caller of F, instead of in F itself.
So if we have, like, say, if F was an R idea of manipulating variables inside of main, we could use this to go back and see if that actually
Yes.
happened.
Yep. And you can see that I can print I. I is a local variable in main. It's not a local variable in F, but I can do it now. And what do you think I should be at this point?
Sure. We haven't planned.
It should be 0 because it's initialized to 0, and this is before we return from F. After we return, it will do the post increment, in the for loop. So it should be 0 at this point.
And the post increment happens right before we re-enter the for loop, right?
It is a part of the for loop, but it is called the post operation. So you have to finish everything in the statement of the for loop first, and then it will go to the post operation, and then it will go back and check the condition again. All right, so I have now examined the value of I. It is 0 as expected, and now I can single step. When you single step, it is always single stepping from the execution point, which is now in function F on line 5, the printf statement. Now, if you single step into printf, it will give you a big, huge mess of stuff, okay? And that's because printf is a huge subroutine. In this case, it's actually translated into puts, which is not really that big. I don't need to single step that. I will just do a next, so I can skip over the printf, and you can see the result of the printf, which is hello here. Now I can use the other command, which is advance, advance, and I want to advance it to the for loop. Do you guys have any questions I can answer? Any particular steps?
No, we got a result. Thank you.
Okay, all right. Yep, go ahead.
After creating a directory, as soon as you type vim to go into the file and create the program, how do I exit that window to the previous one?
To the previous one.
We're making a directory.
How do you exit via?
Back to the command line, you mean?
Yes.
You press the escape key, so you get out of edit mode or insert mode, colon to get to the command prompt of VI itself, and then you either use X to save and quit, or just Q to quit if you have already saved.
Okay.
Lowercase, by the
When
way.
I'm pressing X, it says error 20, mark not set. I'm a total noob to this, so.
Okay. Well, I'm gonna take a look later.
Okay.
Okay. All right. So we now want to advance to a particular line, and I have to go check the line numbers again. And by the way, you can also do a L main. In other words, you can use the label of a subroutine to say where you want to start listing, which is really handy because otherwise you have to look at the line numbers and stuff like that. If you can remember the name of the subroutine, you can use that too. So I want to put a breakpoint. I want to continue execution to line 12. Okay, so we say advance 12, and now we are back to line 12. In other words, it just executed at full speed until we get back onto line 12. So are there any questions at this point? Let's try to print I again, but this time I'm not interested in the value of I. I want to know the address of I. Okay? What is the operator to get the address of something in C and C++? A single ampersand, like so. And so what this is doing is, you can see from the output, it's giving me the address of I, and it will even show you the type. Okay? Int asterisk means it is a pointer to an integer, so the type is correct. This hexadecimal number here, we explained binary numbers today. I didn't quite get to hexadecimal numbers, which is base 16. We'll get to it at some point, but it really is just a huge number. Yep, go ahead.
If we're printing out the address of I, why do we have a pointer? I know a pointer is an address value, but why is it showing us this pointer int when we print out the address?
Because it's the type.
Oh, so it's just
It's just a reminder that you're showing the address of something.
Okay.
In fact, it's a pointer to an integer or an address of an integer.
So that address is an integer stored
It's this
there.
number
and
here.
okay.
No, this is not what is being stored. This is the actual address of the variable.
No. Okay, I know. Yeah, I know.
Yep. Okay, so now we can demonstrate what the X command is going to do. Now, X is a little bit harder to use. If you say help, you can actually get online help within GDB to give you a somewhat terse explanation of the commands. So when you look at this one, it's really kind of terse. It says x/fmt, right here, you specify an address. So the magic has to do with FMT, because X can be used to examine and display things in a variety of formats. In this case, I want to display one thing, and I want that thing to be a half word. Excuse me, a word. W represents a word, and when you look up W, it says it's a word, but a word is not 16-bit. In GDB, a word is 32-bit. Okay, so it's going to treat whatever I'm trying to display as a 32-bit thing. And I want to display it in hexadecimal. So I specify X as the base, or how I want to represent what I'm dumping here. X is hexadecimal. You can also use O for octal, D for decimal signed, and U for decimal unsigned. You can use binary if you want to, float, and so on and so forth. But for the time being, we are just going to use hexadecimal. And then you specify the location, the address of what you want to display. And the address in this case is this thing here. You can either copy and paste, type it over, and guess what? You can also do this.
Would ampersand I would be the same thing? Ampersand I wouldn't be the same?
Ampersand I would do the same thing too. But you can also use a dollar sign. In other words, if this is not just ampersand I is by a long, huge calculation of some kind, you can just refer to the result of that print and say, I want to use that result as the address that I want to display here, which comes in pretty handy. And it shows you that I is currently 0. Okay? In other words, it's displaying the content of I using the address of I in hexadecimal. Are there any questions about the commands that we have just gone through? No questions? You guys are? Yep, go ahead.
Why is that x/1wx? Why is that x/1wx before $2?
Okay, let's go ahead and read this part here. Address is just an expression for the memory address to examine. That is $2. Okay, $2 refers to a result that we have computed before. Format letters are O for octal, X for hexadecimal, D for decimal, and so on. I want it to be in hexadecimal, so I pick X. Size letters are B for byte, H for half word, which is 16-bit. Word is 32-bit. G for 64-bit. I want to dump something that is 32-bit long, so I pick W. And the specified number of objects of the specified size are printed, so you can specify a number by putting it ahead of FMT. So the first thing of FMT is count, which is the number of things that you want to display. Now 1 is implicit. In other words, in this particular case, here, I don't really need to specify this 1. If I specify 2, it will display the same thing as last time, and whatever is after that. So this is a really useful tool when we get to assembly language programming and we are writing subroutines so that those subroutines can interact with C code. This becomes really, really useful because you get to examine what is really around and next to the local variables and parameters and stuff like that. It helps you understand what a frame is and how everything is located relative to the frame pointer and stuff like that. So it will all be handy and useful at some point. Yep.
That's the next word? So
that will be the next word, right. So it will be 4 bytes after the address of I.
And so that's not the address, that's the value that's at those 4 bytes.
Correct. So when you read the output of X, this part tells you the address of the first item that it displays, and then the next item would be like 4 bytes plus the address on the left-hand side. All right. Are there any questions about GDB? Yep.
How do you exit GDB?
Sorry?
How do you exit?
How do you exit GDB? Okay, that's a good question because exit does not work. It's quit.
Oh, okay.
Yep. You can either quit or Control D to get out of GDB. Control D, by the way, represents end of file in Linux. So when you specify end of file, when you're in interactive mode inside GDB, it means you're done. I got nothing else to say. So I'm just going to type Control D here, and it will ask me, do I want to exit? Because the program is still running. That's why it's giving me a warning because I have not exited from this program yet. So if I answer no, I can now continue the execution of the program until it completes. But since I set up a breakpoint, it's breaking every single time. So I'm going to remove the breakpoint. D1 for deleting breakpoint 1. Continue execution at full speed. It finishes the program, and it exits with code 7 because I did not specify a return value in main. So it just picks up some random stuff and say, oh, that's my exit code. Yep.
So you said we can press Control D or we can type in quit?
Yes. So I'm going to type Control D here, and it will still appear quit on the command line,
Okay.
but I just did just a Control D in this case.
And then D1, why are we deleting a breakpoint again?
Because otherwise it will stop every single time I get to line 5.
Oh, okay.
Yeah. And also I can demonstrate that D is in fact the command to delete a breakpoint.
If we have more than one breakpoint, we say D2 or...
Right, because every time you use B to set up a breakpoint, it will tell you what is the number or the ID of that breakpoint. There's probably a command to list all the breakpoints too, but I cannot remember offhand right now. Are there any other questions about GDB other than why are we using something like that? Yep, go ahead.
Which command that we can list all the command we can use?
List.
Yeah,
Listing all the commands.
Listing all the commands?
Yeah.
Of course there's a way to do
I
that.
can't remember. I can't remember.
I'm glad you asked me because now I don't have to explain anything else.
Yeah, I use the help, but it's just a little.
Well, help gives, because there are so many commands in GDB, if you just type help and it shows you all the commands that are available, it will scroll and scroll and scroll and scroll, and it will be hard to find something. So if you're looking for any command that has to do with examining data, okay, then you say help data. And when you type help data, obviously there's more stuff that it can display on one screen full. So that's why it is breaking on one screen. And you can press the enter key to get to the next screen, or you can type Q, enter to quit the showing. So if you pick one particular one, let's see. Let's say disassemble, okay? Then you can just press Q, press the enter key, and then help, and then specify help disassemble, and then it will show you how to use disassemble as a command. Something weird just came to my mind. It has to do with Avengers. Disassemble.
With Ultron? Right.
Yeah, well, I guess Ultron is the ultimate disassembler.
Looks good.
So are there any other questions about how to use GDB? How many people use the debugging ability of code blocks or dev C++? Holy smokes. So how did you guys debug your program? The people who did not use the debugging ability of code blocks or dev C++. I'm just that good. I don't need debuggers. Yep.
Ontos discourages us from using debuggers because of them.
Because what?
When you have an issue with the program, you're just supposed to look at the line number where it's coming from, go there and see if it fixes it. 1,000 errors pop up when they always do. You just have to work it out on your own. Go on discussions and see what other people did.
Okay. Well, in this class, at least in this class, okay, I encourage everyone to learn how to use GDB because it is pretty much the only tool that you have to debug your program. GDB is also useful if you just kind of think back on what we have talked about today. All of those will be useful not only for assembly language programming, but also for regular C, C++ programming. Just the ability to stop and say, okay, I want to stop here and examine the values of the variables. Just that alone is already useful. Now the ability to do backtrace, to basically track back, how did I get here, and also examine the local variables and parameters of every single frame along the way, that is really useful for debugging high-level language programs. So in this class, it is strongly recommended that you use GDB because there's pretty much no other way to debug programs in this class. Yep. Nope. Okay. And GDB is a little bit hard to use because it's a command line kind of thing. It really requires a lot of repeated exposure to do it, to use it. And since we won't be writing any actual assembly language program for the time being, I encourage that if you're taking any other classes like cisp310 or some other C, C++ programming classes, try to use it, okay? Just try to get into the habit of using a debugger. even if you don't use GDB because you prefer to use code blocks or dev C++, they have pretty much equivalent ways of doing things. Okay, setting up breakpoints, I don't think that should be an issue. Examining variables and stuff like that should not be an issue. I don't know exactly how to do the backtrace. I know we can do it. I just cannot remember, the GUI interface of doing it. But getting used to using a debugger is going to be very helpful. We still have quite a bit of stuff to go before we actually start to write code in assembly language. So we have some time in between now and the actual need to use GDB. So I'm hoping that some of you will use this time to practice all of this stuff using a programming language that you are already familiar with. Because otherwise you'll be struggling with a few things. You'll be struggling with the command line, GDB, and on top of that, assembly language itself, and the concepts involved in assembly language programming. And that would not be nice. So you want to get something out of the way as early as possible, so by the time we get to assembly language programming, you can focus on just that. And everything that we talked about today works in C. It will also work in assembly language. Any other questions? Yep.
Can you use GDB for Java?
That is a good question. Because I think there's a GCJ also makes use of GDB. So I'm not sure whether it is applicable.
No, GCP.
Java debugging with GDB. It's possible to debug Java programs compiled with GCJ using GDB. So it is possible, but it's not in general. So you have to use GCJ to compile your Java program, and then whatever bytecode it spits out would be debuggable using GDB. Does Java come with its own debugger, like a command line debugger? It has to. It's probably called JDB or something like that, and probably have very similar features, if not exactly the same kind of features. Any other questions? No other questions? Well, if there are no other questions, we can all go home and have dinner, late dinner, that is. And I think Sushi Cafe is still open. We want to go there. All right, so if there are no questions, I'm going to stop the recorder.
Oh, can you leave it on for a second? I had a quick question.